Hello students, welcome back. The final topic of lesson 9 is the normal approximation of the binomial distribution. Section 4 of this notebook. Here in lesson 9, we did a number of normal approximation problems. As a matter of fact, every single meaningful problem here was a form of a normal approximation. And that's because the key idea here is the central limit theorem, and that is a sort of a normal approximation. No matter which random variable I start with, if I repeat it independently a number of times and take the average, then the probability distribution of that average more or less follows a normal distribution. The normal distribution with the same expected value, the original mean mu, and the new standard deviation of sigma over square root of n, where n is the number of repetitions. Now, new standard deviation, that's a bit too confusing, so we're going to call it standard error, but it does the same thing as the standard deviation. It measures the spread of data or spread of probability. Okay, that was a quick review on the central limit theorem, and let's apply that to binomial distribution. What exactly is a binomial random variable? A binomial random variable is an independent repetition of something called Bernoulli trial, and the Bernoulli trial is extremely simple random variable defined like this. It has only two outcomes: success, failure, and nothing else. And we have probability for success, p, and its complement is the probability of failure. And then the payoff for success is 1, payoff for failure is 0. Perfect for the digital world. Now, it turns out that the mean and the standard deviation for the Bernoulli trial is p and square root of p1 minus p respectively. How is that? I think we did it way back in lesson 5, or maybe in lesson 6, I don't remember. But just in case, let's do it over. Here's the proof, and the expected value is not too difficult. So we have success, and for success, payoff is 1 and probability is p. So we just multiply those two. 1 times p. That's for success. Now for failure, the payoff is 0 and the probability is 1 minus p. So multiply those two together. 0 times 1 minus p, and do your computation. You're going to get p times 0, so the expected value is p, as expected, as was claimed before. Now, how about the standard deviation? That's a bit trickier. Let's calculate the variance. So probability p for success times the deviation, so payoff value minus the expected value squared. That's what we have over here. So probability for success times payoff minus expected value squared. Now how about this? Corresponding value for failure. This is failure probability, 1 minus p. And then payoff minus expected value squared. Alright, we have only two outcomes, so we have only two things to be added there. And then manipulated algebraically. Simplify and then factor the GCF out and simplify. You end up with p, 1 minus p. So take the square root, then you're going to get standard deviation like that. And that is Bernoulli random variable, which corresponds to a single trial, a single roll of a die, for example. Success rate of 1/6 for the ace, and that's going to give me $1. Otherwise, nothing. So failure probability of 5/6. For example, that's one trial. Now, if I repeat it 1,000 times, 2,000 times, that's going to become the binomial random variable. So do it once, that's Bernoulli, and do it multiple times, that's binomial. Multiple times independently. Excuse me. Independence is actually a key. Now, let's apply the central limit theorem here. We have mean and the standard deviation for individual. So if I apply the central limit theorem, what do you get? Mean stay the same, and standard deviation becomes sigma over square root of n, and we can simplify like that. As a matter of fact, here's that computation. You see, sigma over square root of n, that's the central limit theorem, isn't it? Sigma is square root of p over, square root of p1 minus p, and divide by square root of n. Simplify, we get division by n inside of the square root, and that is the SC formula for sampling distribution for sample mean. And by the way, if I multiply by n, then we get, not binomial average, binomial sum. Then binomial sum becomes like this. Just multiply by n, because that's a relationship between average versus sum. Add them all up and divide by n, that's the average. So if I go back, instead of division, multiply by n, that's going to undo everything. So we get this one by multiplying by n. Well, that can wait. The sum can get a little bit trickier, so let's just stick to the averages only. So let's discuss this one, and let's do an example problem about binomial average or sampling distribution of sample means. And we're going to consider the binomial sum or other kind of things in a separate video. Okay, let's keep this. No, not really. Let's keep only this one. Okay, and then let's close all that, and we're going to use this. Now here is an example problem. An urn contains 5 red balls, 3 blue balls, and 2 green balls. Select 50 balls at random with replacement. It's with replacement, so we have independent repetition, so we can use the central limit theorem. Use the sampling distribution of sample mean to estimate the probability that more than a fourth of selected balls are green balls. That is, and this is what this problem is asking, right? Estimate the probability that P of X is greater than 1/4, excuse me. That's what they want. Now, what is the success probability? Well, we are talking about how many green balls. So 2 green balls, that's the important part, and everything else is just non-green. So the probability is P is 2/10, right? And then repetition, we have 50 repetition. And then we can apply this. All right. So expected value is equal to P, so 0.2. And standard error is square root of P and 1 minus that. That is 0.8. And divided by, what's the repetition? 50. That is the standard error, and if you punch in the calculator, you're going to get something. So we have the mean, and then standard error, and then greater than 1/4, well, you have the structure for the normal approximation. What normal picture do we have? So we have an outline like this. And then the expected value, or the mean, is 0.2. That's the center. And then we want greater than 1/4, right? So 1/4 is right here, 0.25. And greater than 1/4, we are looking for this shading. Okay, what's the strategy now? Z-score is end minus center. End is 0.25. And then center is 0.2. And then SE is the square root quantity. Punch your calculator in, you're going to get a certain digit string. Take off the 2 decimal digits, and then look up the Z table. That'll give me the probability, which is the shading to the left-hand side. To get the right-hand side, you'll have to subtract it from 1. All clear? All right. Let's open it. So we have this, and then plug in numbers. We get these for the expected value and the standard error for sampling distribution of sample means. And we want greater than 1/4. Okay, here's the picture. 0.2, that's the expected value, and 0.25 or higher, so right-hand side shading. In order to figure this one out, I need the Z-score here, and let's do the Z-score computation right here. End minus center over SE, or X minus mu over that square root thingy, because that's a standard error. And let me increase the font. So 1/4 minus 2/10, so end minus center. 0.25 minus 0.2, and this quantity, and run your calculator, you're getting 0.88. Look up the Z table from there, and then that's the left-hand side shading. That's going to be the left-hand side shading. So subtract from 1, I'm going to get 1.88 something. And that is the answer we get from this normal approximation through sampling means, the sampling distribution of sample means. The normal approximation of sampling distribution of sample means. All right, we got that. But then again, is this really a good approximation? Well, one way to check it is to use brute force and calculate it through binomial formula. And it goes like this. Binomial 50 choose k, which is 50 factorial over k factorial times 50 minus k factorial. Don't even think about trying to calculate this with handheld calculator. It's not possible. 0.2 to the k power, where power is getting close to 50 power, oh my goodness, and then this one is equally as force, and do your computation and repeat it from 13 to 50, because a quarter is 12.5. A quarter of 50 is 12.5. So add them all up. If you use computer algebra system, you're going to get 0.186, and that's pretty good because previously you got 0.188. The real value is 0.186, so the normal approximation did its job. It was pretty good.